Let's continue with our discussion of active research related to hydrogen absorption in our current day astronomy and astrophysics. So I left off just describing to you the techniques or the experiment for baryonic acoustic oscillations. I'd gotten there first through a description of the power spectrum along 1D sightlines, along the Quasar sightlines, and individually. And part of that process was to generate a probability distribution function, PDF, of the flux values. That's being shown here. They have scientific value in other regimes other than just this P of K or, say, the BAO. So let me describe a few of those. One of them is to... I guess it's not going to work. One of them is to place constraints on the mass of the neutrino. Maybe put the lights down again, if that's okay. Yeah. These are numerical simulations of the IGM, both with and without neutrinos. And the main effect of having these relativistic species is to smooth structure on large scales, suppresses high opacity regions in the high redshift universe. And then these plots, which aren't mine, which makes them, they're not the easiest to see from the back perhaps, show you how the PDF changes. These are relative to a universe with and without neutrinos. So you're supposed to be impressed that as the mass of the neutrinos goes up, there's a tilt here in the ratio between the universe with neutrinos versus one without. That may lead to and can lead to a detectable signature in the PDF of the data. This was applied by Matteo Viel about 5 years ago, and placed constraints on the total mass of neutrinos of about 1 eV. So the shape of the PDF, which you can measure very precisely in the data he used, Ishel spectroscopy, allows an estimate of the upper limit to the mass of the neutrinos, and in principle may even allow a direct mass estimate as well. Another application is to use this PDF to infer properties of the thermal history of the universe and the thermal state of the IGM. I don't know why it's not going to work. Let me go through that. I've shown you previously the temperature over-density relation. This is a little description of how that was derived by Huyn and Ganadian in 1997. They did a calculation of the temperature evolution for a series of fluid elements in a expanding universe. The change in temperature of those fluid elements has a few terms associated with it. A couple of terms related to the adiabatic cooling and heating, which is dominated by the expansion. A term related to the change in internal energy, which is generally small. And a term related to radiative heating and cooling of the gas, which is generally a heating process as you turn on our ionizing sources in the universe. They then solved these calculations semi-analytically and found that the temperature scales like the temperature at the mean density, so some normalization, times 1 plus delta to the gamma minus 1, which I've shown you previously. Sometimes people use beta here. They prefer the notation of gamma minus 1. And on the left-hand side, I'm showing you the comparison between their calculation of temperature as a function of overdensity versus a hydrodynamic calculation that they also performed, just to show that a power law was indeed a very good description. Most of what we're talking about is down here. The departures from the power law at the high overdensity end are related to shock heating in the gas, but those aren't important for the flux statistics that we're talking about. So then the search was on really to determine T naught and gamma from the IGM. Also within their analysis, they emphasized that they could not predict ab initio what those values would be. They depend on the radiative history of the universe, which was unknown then and still, as you've heard throughout the week, is still unknown today as it relates to hydrogen reionization. One approach, and I mentioned this when we were talking about B values the first time, one approach is to assess the widths of the absorption features within the IGM, the B values, and model that with numerical simulations to turn this minimum B value that we can constrain from the data into a constraint on the temperature at the mean density, first well applied by Joop Schij in the late 90s. And he got a rather peculiar temperature profile that hasn't stood up today, but the idea was good. As I'll flip through a few slides on this, on constraining the temperature of the IGM, you'll see the nutshell conclusion is I'm a bit perplexed. I think the community is, but the approaches are improving. Here's a modern version of this, of assessing the b-values. This is top of parameter here as a function of H1 column density, and if you if you do some sigma clipping, which is what they've done in the analysis, there's a clear cutoff in the b-value distribution. Again, tuning that to numerical simulations. These are this is the curves on the left-hand side. This is the prediction from the numerical simulations, and the crossover point is about at a 10,000 degrees temperature here at redshift of 2.4. But the same authors pointed out that this analysis, while it would hold for interpreting the b-value distributions, it was inconsistent with the flux PDF of the same data. More confusion. There are other ways to estimate the temperatures from the curvature of the lines, the shapes of the line profiles, advanced by these authors. It gives you a constraint on both this, the T0 and on gamma. That doesn't agree with the other measurements. Yet another way to do this is with the PDF, as I've mentioned. So here's the PDF that was being used to constrain neutrinos as well. And those authors actually determined or estimated that there's an inverted temperature density relation, gamma of 0.6. It's gamma to the -1 in the exponent. That means a negative exponent. They inferred that from their UV as a shell data. This modern analysis of the BOSS data by KG Lee and collaborators gives a gamma value of 1.6. What's going on? I don't think we still know. There's a lot of, the bottom line is there's enough uncertainty in the modeling and there are degeneracies in the data that we're still a bit flummoxed, and there are paths forward, but stay tuned. This is the state of the affair. I remain confused, and you should too. But that's okay. We'll make more progress. Part of the issue is the degeneracy. You might say, well, maybe you can go to that P of K, our density flux, our power spectrum of density perturbations, and look for the cutoff in that spectrum as a function of K value to identify the temperature. Indeed, that's what is being shown here. This is a nice movie from Alberto Rorai, who's at Cambridge, and modeling what the effects are of just changing T naught. And you can see, indeed, you'd find as you raise up the temperatures, you lose more and more of the power at the small K values, which I mentioned earlier. But the same is true if you vary gamma. This is part of the issue that's going on here. If you vary gamma, you see as well this evolution in the P of K, the power spectrum. So there are degeneracies at play, and resolving them and finding a model that constrains and explains all the data remains to be found. A few slides on hydrogen reionization from the perspective of H1 absorption. First and foremost, the universe is ionized. We started off kind of there. So at redshift 3, we know from the fact that we see a thicket of undulating absorption features that the universe has been ionized. And we infer that the gas is neutral at redshift of 1,000 from the CMB, the fact that what happens in between. The search has been on to understand that. I showed you this slide earlier, the essentially complete opacity at redshift 6 in the IGM, which at least certainly resembles what Gunn and Peterson were thinking of when they talked about the Gunn-Peterson effect almost 50 years ago. That's pretty common. So here's a set of redshift around 6 quasars, and focus on the opacity in the Lyman-alpha forest. Sometimes it's very strong. Sometimes it shows transmission. And so the question really is this tendency of at least some of the quasars, and a significant number of the quasars, to show very high opacities. Is that a signature of hydrogen reionization? It's a difficult question, partly because Lyman-alpha is just the tail that wags the dog. We're really interested in knowing whether the medium has become opaque to ionizing photons, not Lyman-alpha photons. And I'll also remind you that we discussed this at length, that the average effective opacity in Lyman-alpha is increasing rapidly with increasing redshift, even in the ionized universe. Right? So just simply put, if you see what is now an opaque universe in Lyman-alpha at redshift 6, that need not require that the universe has transitioned from highly ionized to neutral. Early estimates from Sloan quasars suggested a departure. So these were the data at the time of the tau effective in Lyman-alpha, down at, say, below redshift 5, and an extrapolation of those data to higher redshifts would be this dashed line, and those authors emphasized that there were a number of quasars now showing opacities that didn't match that extrapolation, and inferred that there had been a phase transition in the IGM, at least amongst some of those sight lines. George Becker pointed out from estimates of the flux PDFs, these are all flux PDFs in a series of high redshift quasars, that the distribution implies a log normal optical depths for the Lyman-alpha forest, and he used that to extrapolate the data at lower redshifts to higher redshifts, and the notion that there were large departures kind of went away. Where we stand today, and George now 8 years later has shown that, or has identified some of these very, let's see, focus on black first, that's the Lyman-alpha absorption, blue is the Lyman beta transmission. He's identified, and several other people have identified these very large troughs, very large swaths. You've seen one, I showed you one earlier, in this opacity that is now understood to be difficult to occur in a random universe, unless patches of that random universe are highly or predominantly neutral. So there is growing evidence, so I think the jury here is also still out from the Lyman-alpha data, that patches of the universe around a redshift of 6 remain neutral, and that you're seeing the real tail end of hydrogen ionization in these patches. Plausible, still work to be done. Another area of research, really changing topics, or more back to maybe the notions of the baryonic acoustic oscillations. We have this IGM that traces the dark matter density field. One can now correlate with that density field any source that you can also just identify at redshifts of 2 or 3, where we have the sensitivity in the IGM. And so Andrew Font in particular has leveraged this to great power using the BOSS data set. And it's just a simple cross-correlation between that dark matter density field inferred from the Lyman-alpha forest with whatever population you may choose. He chose first to use damp Lyman-alpha systems. So there's a cross-correlation between damp Lyman-alpha systems and the IGM. You can see a very positive signal here at small scales in that cross-correlation. You then go forward and infer a bias, so-called bias, in the population of interest here, the DLAs. I won't go through those details, but he infers a high bias of order 2, and then therefore infers that the typical masses may be of order 10 to the 12 solar masses and higher. Right, so this is an approach to, in the case of DLAs, estimate the dark matter halos that are hosting these high regions of high H1 absorption. Whoa, apparently I have a meeting. Somewhere in this world, not in this side of the land. And that I'll remind you, I showed you this morning that we have struggled as a community to identify luminous counterparts. So there's some tension, for sure, in the community between the clustering analysis that is well tested, at least in terms of BAO and some other techniques, and our efforts to find the luminous counterparts of these galaxies. Fun. He applied it to quasars, and also finds a very strong correlation between the halos hosting quasars and the IGM. Here the bias factor is 3.6, which gives you halo masses of order a few times 10 to the 12. That's been inferred previously from the clustering of quasars with themselves, the autocorrelation function of quasars. He points out also a potential asymmetry, that is that the cross-correlation is stronger in that dimension as opposed to along the line of sight, and perhaps may be related to the fact that the quasar is ionizing the gas in front of it and perhaps behind it, as opposed to the side of it. We call that the transverse proximity effect and the line of sight proximity effect. We can apply that to star-forming galaxies, line of break galaxies. Here's the cross-correlation transverse along the line of sight, and there's a putative asymmetry there as well. It's not so obvious in the figure, which suggests infall of material, accretion of gas onto the dark matter halo. And then a comparison of these types of data, again with simulations, give you a halo mass on the order of a few times 10 to the 11 solar masses. Also consistent in this case with the autocorrelation function of these galaxies. Great. Let me show a number of slides now on the circumgalactic medium. I haven't really talked about it so thus far, despite the fact that I work a lot on it. The notion here, but I'll emphasize the hydrogen absorption related to gas around galaxies. So this is a simulation on a halo scale. I think that's probably 1 virial radius, 2 virial radii, 200 kiloparsecs, if you can see the dash in the back of the room, of how gas is, in this case, accreting into a dark matter halo and onto a galaxy in the high redshift universe. And so we wish to explore this and test this in absorption. Of course, we've been discussing techniques to do that in emission, but I'll emphasize the absorption. And that therefore requires we find a background light source, a quasar, primarily, although we can use galaxies, to study the properties of that gas on these scales. And I'll again emphasize the hydrogen. This has been performed rather nicely, I think, at low redshift using HST. I'll explain or emphasize those results first and then go back to the high redshift universe. Here's a targeted galaxy, a red galaxy, at a redshift of 0.2, and then a quasar behind it. And it has nothing to do with the foreground galaxy, of course, redshift 0.6. The separation here is about 90 kiloparsecs, and you then take a spectrum with HST in the ultraviolet of the background quasar to search for signatures of H1 absorption due to the foreground galaxy. You find it even in something that's red, dead, not forming any stars. Here's the Lyman-alpha absorption associated with that galaxy. Here's the zero. Here's the corresponds to the redshift of the galaxy, not the quasar. And I'll emphasize, you actually kind of saw this yourselves. If you look at a redshift 1 or redshift close to 0 here, spectrum of the intergalactic medium, it's very rare to find strong absorption. Okay, the forest is more or less gone. In fact, I have argued that statistically that every one of these strong absorptions are going to be associated with the galaxy in the modern universe. They are, statistically. This, I like these slides a little bit. These summarizes the experiment of the so-called COS Halos project that we've been performing. The x-axis here is the stellar mass. The y-axis here is the specific star formation rate. As I said, that's a red galaxy, so it's massive and has a low specific star formation rate. This gives you a sense of the survey that was performed. There's 43 galaxies. Here's a lower mass star-forming galaxy. You can probably barely make it out in the back. The quasar that lies behind it. Here's about half the sample and the full sample. So ranging from roughly L-star galaxies that are redshift 0.2, not shown here, but is the impact parameters. I'll show you those in a second, but they range from about 30 kiloparsecs to 150 kiloparsecs. Here it is now in terms of the absorption. So I've already shown you that line. It's got an equivalent of over an angstrom, pretty strong line. Here's the absorption related to of hydrogen related to that blue star-forming galaxy. Here's half the systems. I'll pause, but That's maybe could be compared, of course, to some of the real CGM maps that we've been seeing this week, images in H1 Lyman-alpha. Here's the slug again. Here's another substantial jackpot, so-called jackpot nebula around 4 AGN. Here's another one that's coming. So evidence, clear evidence of extended hydrogen around individual galaxies here at redshift 2, not 0.2. But you've seen this, and okay. We see it in absorption, we see it in emission, the gas is clearly there. We could perform the experiment at lower masses, so now I'm going down to almost, 10 to the 8 solar masses, dwarfs if you will, and the specific star formation rate, some dwarfs that are have very little star formation rate, very low star formation rate, some that are clearly forming stars. There's the data for hydrogen absorption of these galaxies. Maybe a little bit higher incidence of non-detections, including some star-forming galaxies. But by and large, even around dwarf galaxies out to their Virgo radius, we see strong and significant hydrogen absorption. The experiment's been performed on Virgo. It's actually been performed on Coma as well. That's just not published yet. Some detections in the outskirts of Virgo. These X's here, they're hard to see, are non-detections. So evidence of depressed absorption towards the center of the cluster, but significant absorption beyond. The experiment is being performed on luminous red galaxies in cycle 23, but we're going to see detections, I guarantee it. Here's the detection of magnesium-2, so a metal around luminous red galaxies as a function of, again, impact parameter, 100 kiloparsecs, megaparsec. The average absorption associated with magnesium-2, where there's magnesium-2, I guarantee you there's hydrogen, so stay tuned. You'll see plenty of that, again, around a luminous red and completely dead galaxy, here now at, say, a redshift 0.6. We can perform the experiment around damp Lyman-alpha systems using quasar pairs. Here's a damp Lyman-alpha system. Here's the hydrogen next to it. All right, you get the picture. Lyman break galaxies. Here's the hydrogen absorption. Yep, right at 0 systemic of the Lyman break galaxies. And even quasars, I'll just skip to there. Here's one of these pseudo maps for quasars. They actually show the strongest average typical hydrogen absorption of any of the phenomena in the universe today. So the takeaway story in terms of the CGM and H1 absorption is yes, yes, yes. Essentially any mass galaxy at any epoch, any star formation rate, it shows a circumgalactic medium that includes significant hydrogen absorption. Oh, great. Any questions on that? Or the previous IGM slides? I'm going to transition for the last roughly 20 minutes here to some of the future work. Yes, Chris?
Can you make any constraints on the total hydrogen column density of that system?
On the total hydrogen column density integrated across the sky, or just sightline by sightline?
Well,
yes, the answer is yes. I just want to know which one you would prefer.
I don't know what you mean.
You asked about column density. So I'm plotting equivalent widths here.
Yeah, column density in those systems.
Right. So I showed briefly the estimates for cost halos. Most of those today have lower limits of around 10 to 16, 10 to 17, lower limits strictly for Lyman-alpha. As I said, we've got new data that covers the Lyman limit. We're far more sensitive. And some of those are at 10 to 17, and quite a few of them are beyond 10 to 19. For the quasars, we have high dispersion data on 10 to 15 such systems. Most of the strong absorbers are around 10 to the 18. So the Lyman-alpha is not damped, but we believe the gas is optically thick. For LBGs, they haven't published, but I don't think they're very high. I bet 10 to the 16 is more typical. And yeah, LRG is coming. The dwarfs, I think characteristic might be more like 10 to 16, 10 to 17. Probably a bit lower.
That's what I was getting at.
Yeah.
What would happen if you made an ionization correction?
Now total hydrogen. Sorry. All right, so we did it right. We measure hydrogen, atomic hydrogen. We infer total. We have to do an ionization analysis to convert atomic hydrogen to total hydrogen. We estimate 10 to the 10 solar masses here and beyond, maybe even 10 to 11 solar masses here, performing that analysis. with slop of at least a factor of 2 because of that ionization correction. It's large. But the masses here are large too. Mm-hmm. All right, so roughly 10 feature paths related to H1 absorption, inspired by the view here. My device. On the horizon, most of what I will describe is on the horizon of 5 years. I don't know. I could give you slides for 10 years, but that's kind of far away. So on the 5 year time scale, some of the things that are being done and will be done that excite me at least. So there's a bias here, of course. One of them is the DESI experiment and the PFS experiment on Subaru. They will be the next massive spectroscopic surveys, at least those that are also focused on quasars. DESI is strictly funded by the Department of Energy in the United States and focused on BAO experiment. And this is the predictions, the forecast, if you will, of how impressively they will constrain that. Across the northern sky. And so all the analyses I was describing about clustering with the IGM, you can do in spades here with the DESI experiment. And PFS, to a lesser degree, that holds true as well. Also the northern sky. IGM tomography, we've heard a little bit about that. This is a burgeoning field. KG Lee's really been leading the effort. The idea here is, as I'll show it more in the next slide, is to use background galaxies, not quasars. Quasars are a bit too rare in the sky to probe scales of, say, of order of megaparsec, so we're using galaxies. And again, the concepts are otherwise similar to some of their techniques. Use the IGM as the flux to give you the density field and identify the morphologies and the distribution of overdensities and underdensities around a redshift of 2 and redshift of 3. And here he's highlighting the putative discovery of a protocluster in the cosmos field, which has also been recognized in galaxy populations. So to show you a bit of the data, because now you are comfortable looking at absorption line data, this is just a shot of the field in one of the in his first paper within the cosmos field, and then here are galaxy spectra, not quasar spectra. Here's the Lyman-alpha forest, right? And again, it's the flux, it's the distribution of the fluxes and principal optical depths that give us the insight into the dark matter density field associated with the foreground universe. That can even be applied to find very rare. This kind of concept can be applied to find very rare features, protoclusters. So this is a simulation. This is a simulation of our protocluster. It has, oh geez, that didn't scale very well. Not too bad. A simulated protocluster, all right, which has a mass of, I think, of order 10 to the 15 solar masses. So it would be a very high mass cluster, quite a high mass cluster in the modern universe. At redshifts of 2 and 3, they're large. They're not collapsed yet. So they cover tens of megaparsecs on the sky. And what Zhang Kai has recognized is that they will make very significant absorption features in IGM spectra, not because of Lyman limit systems or the DLAs. There's no damping here. This is all due to the fluctuating Gunn-Peterson effect, approximation again. And since they cover tens of megaparsecs, that means quite a few arc minutes on the sky. And if you have a survey like BOSS, which or DESI to come, which covers large patches of the sky and has quasar spectra on the orders of megaparsec, you can look for these types of features. These are still simulated here. The Lyman-alpha and Lyman-beta profiles that you should look for. He's done that in the data and has confirmed one case. This is new. So such work is still underway. One case of a protocluster. Here the diamonds indicate 5 quasars from the BOSS survey, where he found these very strong absorption features in the IGM spectra. correlated on the sky, exactly the feature that he was looking for or predicting from the simulation, and then went and did a Lyman-alpha survey, a Lyman-alpha mission survey, to confirm that there's a protocluster there. And that's where this mammoth, crazy mammoth nebula that you see here came from. Lies towards the center of that protocluster. There's work underway to dissect the galaxy halos. So we had this picture for accreting gas, cold stream so-called, onto galaxies. I drew a connection from the simulation side at least between that gas and optically thick gas, Lyman limit systems. One way of testing these scenarios is to look for correlations on tens of kiloparsec scales, halo scales, and one can do that with pairs of quasars. That work's underway. There's actually work, this is actually a spectrum from the HST of a pair of quasars. It's kind of neat looking. Let me explain it. It's a Grism spectrum. There's no slit. So you see the 0th order images, a pair of quasars here, and then you see the spectra. I think that's called 0th order. That's called 1st order. I might have it backwards. And the Lyman limit is actually, if there were a Lyman limit, actually I'm not sure there is one in this case, would be right here at the very blue end of the spectra. And you can look for correlations in the optically thick gas on, this must be, let's see, the separation there is probably just a few arc seconds, probably 30 kiloparsecs. Another application of using galaxies to probe, to dissect other galaxies. This is a background galaxy with enough UV flux that you can get inferences of the gas from its data. Applied by Kate Rubin. It allows you to go in very close to galaxies, which is nice. There's a whole lot of work ramping up with the IFUs. There's a large program on Muse now to look for the galaxy counterparts. So kind of run the experiment the other way. There's a known optically thick gas in the quasar spectrum. Now look for the galaxy counterpart by just paving the sky with spectroscopy. This is not a great, don't even look at the data, the image here. Just listen to me. It's again, we have an interest, what is giving rise to the optically thick gas, or say for even damp Lyman-alpha systems, find the counterparts. A not so cheap, because Muse was tremendously expensive, but a sensible approach is to pave the sky with spectroscopy and look for any associated emission from the galaxies. And there's a large Muse program to do that, and some other smaller programs to do so with damp systems. Coming back to the low redshift universe, this is the probing of galaxies we will have. Now I'm completely out of battery. This is the probing we'll have around galaxies in the kind of redshift less than 0.5 universe. If you can't read it, this is 1 Virgo radius, 2 Virgo radius, 3 Virgo radius. So we will have maps and absorption out to many Virgo radii around galaxies that are both red and dead and star forming and so forth. And you can cut and slice this any way we want. The data is just going to grow here. I showed you ways to get at galaxy gas associations from ALMA. Stay tuned for that. I look forward greatly to Chris Martin's KCWI instrument, so that we'll be doing this in the north and be doing this in the blue to dissect nebulae. It's not so much of an absorption case, but of course, as the link between the two is clear, so indeed. One can use absorption to study the distribution of light around a quasar. I hinted at this when I showed you the Andrew font results. The asymmetry in his cross-correlation. The idea here is to use a background quasar again to probe the H1 absorption around a foreground quasar. So there's a foreground quasar here at 0, which may be emitting isotropically, or which would be this case, which may be emitting primarily towards the observer, which is this case, and then you see enhanced absorption along the side to side in the transverse direction, this transverse proximity effect, and maybe more probably turning off and on, and some combination of the two. And so there's prospects for resolving the duty cycle and anisotropy in the emission of quasars on scales of a few megaparsecs. And wrapping up, what one might do, or this is more of a 10-year thing. One of the things that one might do within a shell spectrometer on the ELTs is yeah, this is kind of a funny figure, is to detect directly the expansion of the universe. So one of the science cases, at least of ESOs, ELT, for the shell, is to take spectra of the intergalactic medium the day it turns on, and then to take spectra of that same intergalactic medium 10 years later, and measure directly the expansion of the universe by looking for very small shifts between the lines. And I think that's what's being plotted here, is the shifts that you would record for a few various cosmologies. Not that we really believe in a couple of them, but that's okay. It still would be a fun experiment to try. And with that, I think I'll conclude. I think we all should thank the organizers for bringing us here in this wonderful place. And I've enjoyed interacting with you over dinner and breakfast and in the hallways. And feel free to contact me anytime if you want to continue the discussion on H1 absorption. Thanks.